April 22, 1945. Colonel Harold Watson stands at the perimeter of a captured German airfield near Munich, his boots crunching on debris-strewn concrete still pockmarked from recent combat. The spring air carries the acrid smell of fuel and burned metal. Around him, American soldiers are securing the facility, but Watson barely notices them. His entire focus is locked on the aircraft sitting before him, gleaming in the late afternoon sun. It's unlike anything he's ever seen. No propeller. No massive radial engine dominating the nose. Just sleek, purposeful lines and two cylindrical pods hanging beneath swept-back wings. The Messerschmitt Me 262. The world's first operational jet fighter. And Watson's orders are as simple as they are terrifying: evaluate it, understand it, and if possible, fly it. Watson is not a regular Army Air Forces officer. He's a test pilot with years of experience pushing American aircraft to their absolute limits. He's flown everything the United States can produce: P-51 Mustangs, P-38 Lightnings, B-17 bombers, experimental prototypes that never made it past the drawing board. He understands aerodynamics, propulsion systems, flight dynamics. He can look at an aircraft and understand what the designers were trying to achieve and where they might have failed. But standing before the Me 262, Watson feels something he hasn't experienced in years: genuine uncertainty mixed with profound respect. This aircraft represents a technological leap so significant that it changes everything he thought he knew about air combat. The Germans haven't just built a better fighter. They've built the fighter of the future, and Watson's job is to steal that future before the Soviets can claim it first. This is the story of Operation LUSTY, Luftwaffe Secret Technology, one of the most consequential intelligence operations of World War II. It's a story of American pilots flying experimental enemy aircraft across a war-torn continent. Of engineers racing against time to capture research data worth more than gold. Of German scientists choosing sides in a new conflict before the old one has even officially ended. And most importantly, it's the story of how aviation leaped forward a full generation in the span of just a few months, transforming from propeller-driven fighters that were already reaching their theoretical limits into jet-powered aircraft that would break the sound barrier and eventually carry humans to the edge of space. Operation LUSTY didn't just document German aviation technology. It preserved it, disseminated it, and ultimately ensured that the jet age would arrive years earlier than it otherwise would have, reshaping both military and civilian aviation in ways that still resonate today. To understand Operation LUSTY's significance, we need to go back several years, to the moment when Allied intelligence first realized the Germans were developing something revolutionary. Throughout 1943, reconnaissance photographs of German airfields began showing anomalies. Aircraft without propellers. Strange wing configurations. Facilities with unusual heat signatures that suggested exotic propulsion systems. Intelligence analysts initially dismissed many of these reports. Jets were theoretical, experimental. Everyone knew that. The British had their Gloucester Meteor, still in early testing. The Americans had experimental jets that barely flew. The idea that Germany, a nation supposedly on the defensive, suffering under constant bombing, struggling with resource shortages, could be fielding operational jet aircraft seemed absurd. But the reports kept coming. Pilots returning from missions over Germany described encounters with impossibly fast interceptors that appeared out of nowhere, made a single devastating pass through bomber formations, then vanished before escort fighters could react. These mystery aircraft could outrun everything in the sky. By early 1944, Allied intelligence could no longer ignore the evidence. The Germans had jet aircraft, and they were operational. The Messerschmitt Me 262 had entered service, initially in small numbers, but growing steadily. German industry, despite being hammered by Allied bombing, had somehow managed to develop, test, and produce a revolutionary new class of fighter. The implications were staggering. If Germany could mass-produce jets before the Allies invaded France, the entire strategic air campaign might be jeopardized. Bomber losses would skyrocket. Fighter escorts would be helpless. Air superiority, the foundation of Allied strategy, would be threatened. But the Germans faced their own challenges. Jet engines were temperamental, requiring exotic materials and precision manufacturing. Fuel was increasingly scarce. And most critically, the German High Command was divided about how to use the Me-262. Some wanted it as a pure fighter. Others insisted it be modified as a bomber. This indecision delayed full-scale deployment long enough for Allied forces to maintain air superiority through D-Day and beyond. As Allied armies pushed across France in the summer and fall of 1944, American intelligence officers began planning for the day they would reach German territory. The air technical intelligence teams had a clear mission: locate, document, and capture German aviation technology before it could be destroyed or fall into Soviet hands. By early 1945, these teams had identified several key objectives. The Me-262 was priority 1, understanding how it worked, how it was manufactured, and most importantly, how it performed. But intelligence reports suggested the Germans had much more. There were rumors of rocket-powered interceptors, experimental bombers, radical wing designs that seemed to defy conventional aerodynamics, flying wings, swept wings, delta wings, variable sweep wings. The Germans appeared to be exploring every possible avenue of aviation advancement simultaneously. Colonel Harold Watson was selected to lead what would become Operation LUSTY in February 1945. Watson was the ideal choice. He had the technical expertise to evaluate complex aircraft systems. He had the piloting skill to fly unfamiliar aircraft safely. And he had the command presence to organize and lead a team operating in chaotic combat conditions. Watson immediately began assembling his team. He needed test pilots, the very best, men who could climb into an enemy aircraft they'd never seen before, figure out the controls, and take off without a manual or any training. He needed aviation engineers who could evaluate manufacturing techniques, reverse engineer propulsion systems, and understand aerodynamic principles from studying physical aircraft. He needed intelligence officers who could track down research facilities and convince or coerce German scientists to cooperate. And he needed logistics specialists who could organize the transport of captured aircraft and documentation from Germany to the United States before the window of opportunity closed. By March 1945, Watson's teams were moving into Germany behind advancing American forces. They operated out of a mobile headquarters that moved forward every few days as new territory was captured. They had a list of priority targets, airfields, research facilities, manufacturing plants, compiled from intelligence reports, interrogations of captured German personnel, and aerial reconnaissance. But they also had to be flexible. In the chaos of a collapsing nation, valuable assets were scattered everywhere. A prototype aircraft might be hidden in a barn. Critical documents might be in an engineer's personal papers. Wind tunnel data might be in a university laboratory hundreds of miles from any military facility. Watson's teams had to be prepared to investigate any lead, no matter how unlikely. The first major discovery came at the Lechfeld airfield complex near Augsburg in late March. American forces captured the facility after brief resistance, and Watson's team was on site within hours. What they found exceeded their most optimistic expectations. Not just one or two Me-262s, but dozens in various stages of assembly and modification. There were standard fighter variants, reconnaissance versions stripped of weapons and optimized for speed, and even experimental models with different engines and wing configurations. More importantly, the Germans had evacuated so quickly that they left behind documentation, maintenance manuals, flight characteristics reports, even some engineering drawings. For the first time, Watson's team had actual German documentation on how to operate a jet aircraft. Watson assigned Captain Robert Straubel to make the first flight evaluation of a captured Me-262. Straubel was one of the most experienced test pilots in the Army Air Forces, a calm, methodical flyer who had survived dozens of test flights in experimental American aircraft. But even Straubel felt apprehensive as he approached the Me-262 that cool April morning. The aircraft was beautiful in a stark, functional way. Its fuselage was narrow and streamlined. The wings swept back at a noticeable angle, reducing drag at high speeds. The two Junkers Jumo 004 turbojet engines hung in nacelles beneath the wings, positioned to keep their weight close to the aircraft's center of gravity. The cockpit canopy was well designed, offering excellent visibility. But every detail reminded Straubel that he was looking at an aircraft designed by enemy engineers, built in enemy factories, intended to kill his countrymen. Now he was going to fly it. Straubel spent an hour doing his pre-flight inspection, examining every detail with the help of a German mechanic who had surrendered with the airfield and was cooperating with American forces in exchange for decent treatment. The mechanic explained the engine starting sequence, the fuel system, the electrical systems. He warned Straubel about the engine's temperamental nature, advanced the throttles too quickly and they would flame out, requiring an emergency landing. Throttle them back too suddenly, and the same thing would happen. The Jumo 004 engines required smooth, gradual inputs. They were also incredibly loud when starting, producing a high-pitched whine that was utterly different from the roar of a conventional piston engine. The mechanic explained that each engine had a service life of only about 25 hours before it needed complete replacement. The turbine blades, made from lower-quality materials due to wartime shortages of heat-resistant alloys, simply couldn't withstand the temperatures and stresses for longer than that. Straubel climbed into the cockpit, settled into the seat, and began his checklist. The instrument panel was entirely in German, but the basic flight instruments were universal: airspeed indicator, altimeter, artificial horizon, compass, engine temperature, and pressure gauges. The German mechanic stood on the wing, pointing out the critical instruments and controls. Here was the throttle quadrant, with separate levers for each engine. Here was the landing gear control. Here was the trim adjustment. The gun sight was still installed, but the ammunition had been removed. Straubel took a deep breath, then signaled the ground crew. They had rigged an external battery to assist with starting, since the aircraft's internal batteries were weak. Straubel moved the engine controls through the starting sequence the mechanic had taught him. The right engine began to spool up with that distinctive jet whine, completely different from any aircraft sound he'd heard before. White smoke poured from the exhaust as fuel ignited. The engine stabilized at idle, the whine settling into a steady pitch. Straubel repeated the process with the left engine. Both engines were now running, consuming fuel at a rate that seemed absurdly high to a pilot accustomed to piston engines. Straubel released the brakes and the Me-262 began to roll forward. The acceleration was immediate and dramatic. Unlike a propeller-driven fighter, which needed to build up speed gradually as the propeller bit into the air, the jet engines produced constant thrust regardless of airspeed. The Me-262 accelerated smoothly, steadily, rapidly. Straubel had been briefed that the aircraft needed high takeoff speed, around 110 miles per hour, before it had enough lift to fly. He watched the airspeed indicator climb, 60 miles per hour, 80, 100. The runway was disappearing rapidly beneath him. At 115 miles per hour, Straubel gently pulled back on the control stick and the Me-262 leaped into the air. The rate of climb was astonishing. In seconds he was passing through 1,000 feet. The aircraft wanted to climb steeply, and Straubel had to push forward on the stick to level off and build up more speed. At 300 miles per hour, the Me-262 felt stable and responsive. Straubel tried a gentle turn, banking the aircraft smoothly. The controls were well harmonized, requiring reasonable force but responding crisply. He climbed to 10,000 feet and leveled off, then carefully advanced the throttles further. The acceleration was immediate. 350 miles per hour. 400, 450. The Me-262 was still accelerating smoothly with no buffeting or vibration. At 500 miles per hour, Straubel was flying faster than he'd ever flown in his life, faster than any Allied aircraft could fly in level flight, and the Me-262 felt stable and controlled. The realization hit him with full force. This aircraft had been in combat for months, shooting down American and British bombers, and the Allies had nothing that could catch it. Every bomber pilot who had watched an Me-262 flash through their formation was facing an aircraft that was simply superior to anything escorting them. But Straubel also noticed the problems immediately. The engine response was sluggish. When he moved the throttles, there was a noticeable delay before the engines responded. In a dogfight, that delay could be fatal. The aircraft handled poorly at low speeds, feeling mushy and unresponsive when Straubel throttled back below 250 miles per hour. The Germans had clearly optimized it for high-speed interception, not low-speed maneuvering combat. And the fuel consumption was enormous. The gauges were visibly dropping even after just 15 minutes of flight. Straubel flew for 30 minutes total, testing the aircraft's handling at different speeds and altitudes, then prepared for what he knew would be the most dangerous part of the flight, landing. German pilots had developed specific procedures for landing the Me-262, and Straubel had memorized them from the documents Watson's team had captured. Keep the speed high on approach. Too slow and the aircraft would stall without warning. Don't reduce power too quickly or the engines would flame out. Plan for a long landing roll because the aircraft touched down fast. Straubel set up his approach, keeping the airspeed at 160 miles per hour until he was certain he could reach the runway, then gradually reducing power and speed. At 120 miles per hour, he crossed the runway threshold. At 110, he flared gently and the main wheels touched down. The Me-262 rolled for what seemed like forever before Straubel could safely apply brakes and slow to taxiing speed. As he turned off the runway and headed back to the parking area, Watson was already running toward the aircraft, a film crew behind him frantically capturing footage of the first American flight of a captured German jet. Straubel's debriefing took hours. What were the handling characteristics at different speeds? How did the aircraft respond to control inputs? What were the visibility issues? How difficult was the engine management? Could average pilots learn to fly it with training? Straubel's assessment was both enthusiastic and cautious. The Me-262 was an incredible aircraft, leagues ahead of anything the Allies had. Its high-speed performance was extraordinary. But it was also specialized, designed for high-speed interception, not dogfighting. It required skilled pilots who understood energy management and could adapt to the sluggish engine response. And it was mechanically complex, requiring extensive maintenance and suffering from short engine life. In the hands of expert pilots with adequate support, it was devastating. In the hands of average pilots, or without proper maintenance, it was vulnerable. Over the following days, other members of Watson's team flew the Me-262 and additional aircraft that had been captured. Each flight provided new insights. They discovered that the Me-262's swept wings, which had seemed like an aesthetic choice, were actually a critical aerodynamic feature. The sweep reduced the effects of compressibility at high speeds, allowing the aircraft to fly faster than would otherwise be possible. They learned that the engines required very specific operating procedures. There was a narrow band of acceptable throttle positions and rates of change. Violate those limits and the engines would surge, stall, or even catch fire. They found that the aircraft's landing gear was a weak point. The nose gear in particular was fragile and prone to collapse if the pilot came down too hard. But Watson's teams weren't just flying captured aircraft. They were also beginning to uncover the broader scope of German aviation research, and what they found was both impressive and alarming. At a facility near Oberammergau, they discovered documentation of swept-wing research dating back to 1940. German engineers had systematically studied how wing sweep affected performance at different speeds, using wind tunnels to test dozens of configurations. The data they had accumulated was extraordinarily valuable. It represented years of research that Allied engineers hadn't even begun. The Germans had determined that wings swept back at angles of 30 to 45 degrees dramatically reduced drag at transonic speeds, speeds approaching the sound barrier, allowing aircraft to fly faster with the same amount of power. This research explained why the Me-262's wings were swept, and it would revolutionize post-war aircraft design. At another location, Watson's team found the Arado AR-234, the world's first operational jet bomber. The AR-234 was sleek and purposeful, designed for high-speed reconnaissance and bombing missions. With a top speed of over 460 miles per hour, it could outrun virtually any Allied fighter. The aircraft had actually been used operationally during the final months of the war, conducting reconnaissance missions over Allied positions and even bombing attacks during the Battle of the Bulge. German crews reported that the AR-234 was nearly immune to interception. Allied fighters simply couldn't catch it at altitude. The AR-234 used the same Jumo 004 engines as the Me-262, mounted on stub wings under the fuselage. Its range was limited, but for the missions it was designed for, fast reconnaissance and precision bombing, it was remarkably effective. Watson immediately recognized the AR-234's significance. If jet bombers could routinely outrun fighters, the entire concept of air defense would need to be rethought. Interceptors would need to be faster, would need better radar and fire control systems to allow them to engage targets with closure rates measured in hundreds of miles per hour. The bomber would no longer be always getting through because defenses couldn't stop it. Instead, the bomber would be getting through because it was too fast to catch. This realization would shape post-war strategic thinking and accelerate the development of jet interceptors and surface-to-air missiles. Then came perhaps the most shocking discovery of all. At a facility near Bad Schwischen, American forces found the Messerschmitt Me 163 Comet, and with it, documentation and testimony from German pilots who had actually flown this extraordinary aircraft in combat. The Me 163 was unlike anything Watson's team had encountered. It was tiny, just over 19 feet long with a wingspan of only 30 feet. It looked more like a stubby glider than a fighter aircraft. But appearances were deceiving. The Me 163 was powered by a Walter HWK 109-509 rocket engine that burned a hypergolic mixture of concentrated hydrogen peroxide and a hydrazine hydrate/methanol solution. When these two chemicals mixed, they ignited spontaneously, producing thrust that could propel the tiny aircraft to nearly 600 miles per hour and allow it to climb to 30,000 feet in less than 3 minutes. The German pilots who briefed Watson's team on the Me 163 spoke with a mixture of pride and terror. The aircraft was exhilarating to fly. The acceleration was like nothing else in aviation, pinning the pilot to his seat as the rocket engine thrust the aircraft skyward at an angle that felt nearly vertical. At full power, the Me 163 could outrun anything in the sky and could reach bomber altitudes faster than any other interceptor. But it was also extraordinarily dangerous. The rocket fuel was so corrosive that ground crews handling it wore full protective gear. Any leak or spill could cause severe chemical burns. Several German pilots had been killed not in combat but from fuel leaks that dissolved their flight suits and burned their flesh. The aircraft had only about 8 minutes of powered flight before the fuel was exhausted. At that point, it became a glider with a very poor glide ratio. And the landing was perhaps the most dangerous part of the entire flight. The Me 163 had no conventional landing gear. It took off from a wheeled dolly that was jettisoned immediately after takeoff to reduce drag. Landing was accomplished on a retractable skid mounted under the fuselage. The pilot had one chance to get it right: come in too fast and the aircraft would bounce and potentially flip over; too slow and it would stall and drop in, likely destroying the aircraft and killing the pilot. German pilots described landing speeds of around 110 miles per hour, with the pilot essentially flaring just above the ground and letting the Me 163 settle onto the skid, then skidding to a stop. The impact could be severe enough to cause spinal injuries. Despite these dangers, the Me 163 had achieved some combat successes, and German engineers had been working on improved versions with longer range and better handling when the war ended. Watson knew that flying in Me 163 would be extraordinarily risky, but he also knew that the intelligence value would be immense. Understanding how rocket propulsion worked in a manned aircraft, how pilots coped with the extreme acceleration and limited powered flight time, and how the aircraft handled at speeds approaching 600 miles per hour would be invaluable. He assigned the test flight to Captain Eric Brown, a British Royal Navy test pilot who had been attached to Watson's team. Brown was one of the most experienced test pilots in the Allied forces, and he had a reputation for being able to fly anything. Even Brown was nervous about the Me-163. He spent days studying the aircraft, talking with German pilots and ground crew, reviewing every piece of documentation Watson's team had captured. On a clear morning in early May 1945, just days after Germany's formal surrender, Brown prepared for his flight. The Me-163 had been fueled, a process that required extreme caution as the two fuel components were kept in separate tanks and mixed only in the combustion chamber. Ground crews stood well back, wearing protective equipment. Brown climbed into the cramped cockpit, barely large enough for him and his parachute. The instrument panel was basic: airspeed, altitude, a timer showing remaining fuel, and engine indicators. Brown ran through his checklist, then signaled the ground crew. They triggered the engine ignition sequence. There was a moment of silence, then a tremendous roar as the rocket engine ignited. Brown felt the incredible thrust immediately, pushing him back into his seat. He released the dolly and the Me-163 shot forward like a bullet, accelerating so violently that Brown could barely process what was happening. The aircraft rotated almost immediately, climbing at what felt like an impossible angle. In less than 2 minutes, Brown was at 20,000 feet and still climbing rapidly. The fuel gauge was dropping just as fast. He leveled off briefly to test the controls, finding the aircraft responsive and stable at high speeds. Then he put it into a shallow dive, accelerating to nearly 550 miles per hour, faster than he or any other Allied pilot had ever flown. The Me-163 was rock solid, with no buffeting or vibration. But the fuel gauge was now critically low. Brown had perhaps 2 minutes of powered flight remaining. He began a wide, descending turn back toward the airfield, then shut down the rocket engine to conserve the last of his fuel in case he needed it. The sudden silence was shocking after the continuous roar of the rocket. The Me-163 was now a glider, and not a particularly good one. Brown needed to carefully manage his energy, trading altitude for distance, ensuring he had enough height to reach the airfield but not so much that he would overshoot. As the airfield came into view, Brown set up his approach. He extended the landing skid, confirmed it was locked in place, and focused on his airspeed and altitude. Too high, too fast, he deployed the speed brakes, panels that extended from the fuselage to increase drag. The airspeed began dropping. He was now committed. There would be no go-around, no second chance. At 110 miles per hour, he flared gently and the Me-163's skid hit the runway with a jarring impact. The aircraft bounced slightly, settled back down, and skidded to a stop in a cloud of dust. Brown sat in the cockpit for a moment, adrenaline still surging, then unbuckled and climbed out. Watson and his team rushed forward, film cameras capturing the historic moment. Brown had just become the first Allied pilot to fly a rocket-powered aircraft, and he had demonstrated that the Me-163, despite its dangers, was a viable weapons system that pointed toward the future of high-speed aviation. As May turned to June, Watson's teams were discovering new aircraft almost daily. At one facility, they found the Heinkel He-162 Volksjäger, a lightweight jet fighter built primarily from wood due to wartime material shortages. The He-162 was a desperate attempt by German leadership to create a people's fighter that could be mass-produced quickly and flown by Hitler Youth members with minimal training. The concept was as absurd as it was tragic, taking teenagers with barely any flight experience and putting them in a high-performance jet fighter. The He-162 itself was actually a decent design in some respects, with clean aerodynamics and adequate performance. But it had been rushed into production with inadequate testing, and the wood and glue construction was prone to failure. The glue, made from inferior wartime materials, would dissolve or come apart under stress, causing structural failures. Several German test pilots had been killed when their He-162s simply broke apart in flight. At another location, Watson's team discovered something that would influence aviation design for decades: the Horten Ho 229, a jet-powered flying wing. The Horten brothers, Reimar and Walter, had been experimenting with flying wing designs since the 1930s, believing that eliminating the conventional fuselage and tail could reduce drag and improve performance. The Ho-229 was their most ambitious design, a pure flying wing powered by two Jumo 004 jet engines mounted inside the wing. The aircraft that American forces captured was actually the third prototype. Earlier versions had crashed during testing, killing one test pilot. But the surviving aircraft showed remarkable promise. Its radical design reduced drag significantly, potentially giving it greater range and speed than conventional aircraft with the same engines. More intriguingly, the Horton brothers had used a mixture of sawdust and charcoal in some of the aircraft's skin panels, which they claimed would absorb radar waves, making the Ho-229 possibly the world's first stealth aircraft, though whether this was intentional or coincidental remains debated by historians. The Ho-229's significance wasn't immediately obvious to Watson's team, but aviation engineers who studied it later realized it represented a completely different approach to aircraft design. The flying wing configuration would eventually lead to aircraft like the B-2 Spirit stealth bomber, which shares the Ho-229's basic configuration though with vastly more sophisticated technology. In 1945, however, the Ho-229 was viewed primarily as an interesting experiment, too radical, perhaps too risky, but containing principles that might be useful in future designs. Watson's teams also discovered extensive documentation of German wind tunnel testing. At facilities in Braunschweig and Göttingen, they found wind tunnels and mountains of test data covering virtually every aspect of high-speed aerodynamics. German engineers had systematically tested wing shapes, fuselage configurations, control surface designs, and engine intake geometries. They had explored the transonic region, speeds approaching the sound barrier, where compressibility effects caused strange and dangerous phenomena. Allied engineers knew about compressibility but hadn't studied it systematically. The Germans had, and their data showed exactly what happened to different wing shapes at different Mach numbers, how shock waves formed and affected performance, and how to design aircraft that could safely approach and potentially exceed the speed of sound. This wind tunnel data was, in many ways, more valuable than the actual aircraft. An aircraft showed you what was possible. The research data showed you why it was possible and how to improve upon it. With German wind tunnel data, American engineers could skip years of testing and move directly to designs optimized for high-speed flight. This single factor, access to German research data, would accelerate American aviation development more than any other aspect of Operation LUSTY. But capturing this technology was only half the battle. Watson and his teams now faced the challenge of getting it out of Germany before the occupation zones were finalized. The agreements reached at Yalta and later Potsdam divided Germany into 4 occupation zones: American, British, French, and Soviet. Once those zones were formally established, movement between them would be restricted. Aircraft and equipment in the Soviet zone would remain there, under Soviet control. And the Soviets, like the Americans, understood the value of German aviation technology. Soviet technical intelligence teams were conducting their own operation, nearly identical to LUSTY, racing to capture German aircraft, documentation, and engineers before the Americans could reach them. Watson coordinated with Military Logistics Command to organize a massive airlift operation. Aircraft that could fly would be flown out by American pilots, despite the risks of flying experimental, barely understood aircraft hundreds of miles across war-torn Europe. Aircraft that couldn't fly or were too valuable to risk would be disassembled and shipped. The logistics were nightmarish. The Me-262s required special fuel and constant maintenance. Each aircraft needed its engines checked after every few hours of flight, with regular engine replacements. The AR-234 was too large to fit in standard transport aircraft and had to be carefully disassembled. The Me-163 couldn't be flown at all. The rocket fuel was too dangerous to transport, and without fuel, it was just an unpowered glider. Documentation had to be catalogued, packed, and shipped. German engineers who wanted to cooperate, and many did, preferring American captivity to Soviet, had to be processed and transported. One of the most dramatic moments came in early June when Watson received intelligence that an experimental Messerschmitt aircraft was located at a facility near Oberammergau, which was about to be transferred to French control. The aircraft was reportedly a prototype with variable sweep wings that could be adjusted to different angles for different flight conditions. Watson immediately dispatched a team to investigate. They arrived to find the prototype, designated P.1101, sitting in a partially destroyed factory building. The aircraft was incomplete, it had never flown, but its significance was immediately apparent. The wings could be manually adjusted on the ground to different sweep angles: 35 degrees for takeoff and landing, 40 degrees for cruise, 45 degrees for high-speed flight. The designers hadn't figured out how to make the sweep adjustment work in flight. That would require hydraulic systems and controls that were beyond wartime German engineering capabilities, but they had proven the concept worked. Watson's team disassembled the P.1101 in less than 24 hours, working through the night by portable generator lights. They packed it onto trucks and drove it to an American airbase, reaching safety just hours before French forces arrived to take control of the area. The P.1101 would eventually be shipped to the United States, where engineers would study it intensively. The concept of variable sweep wings would evolve into swing-wing designs like the F-111 and F-14, aircraft that could adjust their wing sweep in flight for optimal performance at different speeds. By July 1945, Watson's teams had catalogued and captured dozens of aircraft representing virtually every aspect of German jet aviation research: operational fighters like the Me-262, experimental interceptors like the Me-163, jet bombers like the AR-234, radical designs like the Ho-229, and numerous prototypes that never reached production. They had captured thousands of pages of documentation, engineering drawings, wind tunnel data, test flight reports, manufacturing specifications. They had identified and begun interviewing hundreds of German engineers and scientists, many of whom were willing to share their knowledge in exchange for protection from prosecution and the opportunity to continue their research under American sponsorship. The captured aircraft and equipment began arriving at Freeman Field in Seymour, Indiana, which had been designated as the primary repository for German aviation technology. Transport aircraft delivered disassembled jets in carefully packed crates. Ships docking on the East Coast carried engine components, documents, and complete aircraft that had been too large or too fragile to fly across the Atlantic. And American pilots ferried flyable aircraft across the ocean, hopping from Iceland to Greenland to Newfoundland, nursing temperamental German jets across thousands of miles of open ocean. It was an unprecedented logistical achievement, moving dozens of aircraft and tons of equipment halfway around the world in a matter of months. At Freeman Field, Watson established a comprehensive evaluation program. Each captured aircraft would be thoroughly examined by engineers, then flight tested by multiple pilots to determine its performance characteristics, handling qualities, strengths, and weaknesses. The goal wasn't just to understand what the Germans had built, but to learn how to build better aircraft using the principles they had discovered. American aviation companies sent their top engineers to Freeman Field to study the captured aircraft. Representatives from Lockheed, North American Aviation, Douglas, Boeing, and others carefully examined German jets, took measurements, studied construction techniques, and most importantly, studied the aerodynamic principles that made them work. The impact on American aircraft design was immediate and profound. North American Aviation had been working on a jet fighter design designated FJ-1 Fury, with straight wings and conservative aerodynamics. After their engineers studied the German swept-wing research data captured by Operation LUSTY, they completely redesigned the aircraft. The result was the F-86 Sabre, with wings swept back at 35 degrees, an angle derived directly from German research. The F-86 would become one of the most successful fighter aircraft of the early jet age, dominating Korean War skies and demonstrating that American engineers had learned their lessons well. Boeing engineers studying the Arado AR-234 and German bomber research began to understand how jet propulsion could revolutionize strategic bombing. They started work on the B-47 Stratojet, which would feature a radical design with 6 jet engines, swept wings, and high-altitude performance that made it nearly immune to interception. The B-47 entered service in 1951, and became the backbone of Strategic Air Command's nuclear deterrent force. Its design influenced the even larger B-52 Stratofortress, which followed the same basic configuration and is still flying today, more than 7 decades after its first flight. Both aircraft owed their existence in large part to German research captured during Operation LUSTY. The rocket technology captured with the Me-163 program fed into American rocket development, though this overlapped significantly with Operation Paperclip, the better-known program that brought German rocket scientists like Wernher von Braun to the United States. But the line between aviation and rocketry was blurring. Understanding how rocket engines worked, how to handle hypergolic fuels, how to design aircraft that could withstand extreme acceleration, all of this was relevant to both fields. The X-1, the aircraft that would break the sound barrier in 1947, used a rocket engine derived from German technology. Later X-planes that explored hypersonic flight and the edge of space all built on foundations laid by German wartime research. But Operation LUSTY's influence extended beyond just copying German designs. Perhaps more importantly, it fundamentally changed American approaches to aviation research and development. Before the war, American aviation had advanced incrementally. Each year's fighters were slightly better than the previous years, with modest improvements in speed, range, and capability. The discovery of German jets shattered this complacency. It demonstrated that revolutionary advances were possible, that taking bold technical risks could lead to generational leaps in performance. After Operation LUSTY, American aviation research became more ambitious, more willing to explore radical concepts, more focused on achieving breakthrough performance rather than incremental improvement. The experimental X-plane program, which began in the late 1940s, exemplified this new approach. Rather than designing practical aircraft for immediate military use, the X-planes were pure research vehicles designed to explore specific technical questions. How do aircraft behave at transonic speeds? What happens at supersonic speeds? How high can aircraft fly? Can humans survive the extreme accelerations and environments of hypersonic flight? This systematic exploration of flight regimes beyond what was currently possible reflected a philosophy that Operation LUSTY had validated. Sometimes the path to practical applications runs through seemingly impractical experiments. The German engineers who cooperated with Operation LUSTY and later came to the United States through various programs made significant contributions to American aviation. While many of the most famous scientists, like Wernher von Braun, were focused on rockets and missiles, numerous aerodynamicists, jet engine specialists, and aircraft designers brought their expertise to American companies and research institutions. They brought not just technical knowledge but a different design philosophy. German engineers had been forced by wartime desperation and resource constraints to think creatively, to challenge conventional assumptions, to pursue radical solutions when conservative approaches weren't enough. This willingness to embrace unconventional thinking was infectious, influencing a generation of American engineers who worked alongside them. One of the most significant German contributions was in the field of boundary layer control and high-speed aerodynamics. German researchers had made tremendous advances in understanding how air behaves at high speeds, how shock waves form and propagate, and how to design aircraft surfaces that minimize drag and maximize stability. This research was crucial for developing aircraft capable of supersonic flight. American engineers studying German wind tunnel data discovered solutions to problems they hadn't even fully understood yet. The data showed them what would happen when aircraft approached the speed of sound, how control surfaces would behave differently at transonic speeds, and how to design wings and fuselages that could transition smoothly through the sound barrier without catastrophic instability. The integration of German engineers into American aviation wasn't without controversy. Many Americans resented working alongside men who had, until recently, been the enemy. Some German engineers had been members of certain political organizations during the war, raising ethical questions about their recruitment. The decision to bring German scientists and engineers to the United States was pragmatic rather than idealistic. American military and political leaders believed that denying the Soviet Union access to German expertise was more important than concerns about the individual's wartime activities, provided they hadn't been directly involved in atrocities. This calculated pragmatism would characterize much of the early Cold War, where former enemies became valuable assets in the emerging conflict with the Soviet Union. The Soviet Union, meanwhile, had conducted its own massive operation to capture German aviation technology. Soviet forces had overrun much of eastern Germany, including important research facilities and production plants. They had captured their own collection of Me-262s, jet engines, wind tunnel facilities, and documentation. They had also captured or recruited hundreds of German engineers, sometimes forcibly. The Soviets took a different approach than the Americans. Rather than immediately integrating German technology into their own designs, they initially focused on direct copying. Soviet engineers reverse-engineered captured German jet engines, producing near-exact copies designated as Soviet designs. The Klimov VK-1 engine, which powered early Soviet jets like the MiG-15, was essentially a copy of the British Rolls-Royce Nene engine, but Soviet engineers had learned how to build it by studying captured German turbojets first. This parallel acquisition of German technology by both superpowers created a strange symmetry in Cold War aviation. Both American and Soviet jet fighters of the late 1940s and early 1950s showed clear German influence: swept wings, jet engines, aerodynamic principles derived from German research. When American F-86 Sabres met Soviet MiG-15s in combat over Korea, it was in some ways a contest between two different interpretations of German aviation technology. The F-86 emphasized pilot visibility, control harmony, and ease of handling. The MiG-15 prioritized raw performance, climb rate, altitude capability, and heavy armament. Both were swept-wing jets with similar performance envelopes. Both traced their lineage back to German research captured in 1945. The battles between them would determine which approach, American or Soviet, had better understood and applied the lessons of German jet aviation. The Korean War, which began in June 1950, became an unexpected proving ground for Operation LUSTY's legacy. Just 5 years after Watson's teams had first flown captured Me-262s, American pilots were flying F-86 Sabres that embodied everything learned from German jets. The Sabre's 35-degree wing sweep, its high-speed stability, its transonic performance characteristics, all reflected German research. Similarly, the MiG-15s that opposed them demonstrated Soviet understanding of the same principles. The dogfight's over. Megali, the airspace near the Yalu River where most jet combat occurred, were fought between aircraft that would not have existed without Operation LUSTY and its Soviet equivalent. American pilots flying F-80SIXs discovered that their aircraft had better control response at high speeds, superior visibility from the cockpit, and handling qualities that made it easier to track targets in maneuvering combat. The MiG-15 could climb faster and had heavier armament, but it was less stable at high speeds and harder to control in high-G maneuvers. These differences reflected not just the aircraft themselves but the philosophies behind them. American designers had prioritized creating an aircraft that good pilots could use to maximum effect, while Soviet designers had prioritized raw performance numbers. The F-80SIX's kill ratio over the MiG-15, generally estimated at somewhere between 7-1 and 10-1, suggested that the American approach had been more successful, though pilot training and experience also played crucial roles. Back in the United States, the aircraft captured during Operation LUSTY were being systematically studied, flown, and in some cases, destroyed through testing to failure. Engineers wanted to understand not just how German jets performed but also where their limits were. Me-262s were flown until their engines failed, providing data on engine reliability and maintenance requirements. Structures were tested to destruction to understand stress limits and failure modes. Every piece of data was catalogued and added to the growing body of knowledge about jet aviation. Some of the captured aircraft were displayed publicly. The Army Air Forces organized exhibitions where American citizens could see German jets up close, understand what their military had faced, and appreciate the technological achievement that Operation LUSTY represented. These public displays served multiple purposes. They boosted morale by showing that American forces had captured enemy technology. They educated the public about the changing nature of warfare. The propeller age was clearly over, and the jet age had arrived. And they helped justify the enormous defense budgets that would be needed to develop American jets capable of matching or exceeding what the Germans had achieved. The Cold War was beginning, and public support for military spending would be crucial. Showing citizens actual German jets helped make the case that America needed to invest heavily in aviation research to avoid being left behind. As the late 1940s progressed into the 1950s, Operation LUSTY's direct influence began to fade, but its indirect influence continued to shape aviation development. American engineers had fully absorbed the lessons of German research, and were now pushing beyond it. The X-1 broke the sound barrier in 1947, achieving what many German engineers had thought might be impossible. The X-2 explored even higher speeds in the early 1950s. American jet fighters like the F-100 Super Sabre exceeded the speed of sound in level flight, something no German aircraft had achieved. American bombers like the B-52 could fly faster, higher, and farther than any German design had contemplated. But all of these achievements built on foundations laid by German wartime research and preserved by Operation LUSTY. The swept-wing configuration that German research had validated became standard on virtually all high-performance aircraft. When engineers at Boeing designed the 707, America's first successful jet airliner, they gave it swept wings derived from the same principles that had shaped the B-47 bomber, which in turn came from German research. The 707's commercial success launched the jet age in civilian aviation, leading to the mass air travel that we take for granted today. Every time a commercial airliner takes off with swept wings, it's carrying forward a design principle that German engineers validated and that Operation LUSTY preserved for the world. The delta wing configuration, another German innovation that had been explored in wartime research, found application in supersonic aircraft. The Convair F-102 and F-106 interceptors used delta wings for high-speed performance. The legendary Concorde supersonic transport used a modified delta wing. Even the Space Shuttle, decades later, would use a delta wing configuration for its atmospheric re-entry and landing. These designs all trace their lineage back to German research that explored alternatives to conventional wing shapes. Variable sweep wings, first explored in the German P.1101 that Watson's team had captured just hours before it would have been lost to French control, eventually led to successful swing-wing designs. The F-111, which first flew in 1964, could sweep its wings from 16 degrees for takeoff and landing to 72.5 degrees for supersonic flight. The F-14 Tomcat, which became one of the Navy's most successful fighters, used variable sweep wings to combine excellent low-speed carrier landing characteristics with supersonic performance. The Soviet Union developed its own swing-wing designs, including the Tu-160 bomber and the MiG-23 fighter. All of these aircraft owed their basic configuration to German research preserved by Operation LUSTY. Rocket propulsion, first encountered operationally in the Me-163, evolved into a critical technology for both military and space applications. American interceptors like the F-104 used rocket-assisted takeoff to achieve better performance. More significantly, rocket technology became the foundation of the space program. The rockets that would eventually carry humans to the moon built on principles that German engineers had explored in their wartime desperation to create high-performance interceptors. The line from the Me-163's Walter rocket engine to the Saturn V that powered Apollo missions was surprisingly direct, running through Operation Paperclip's capture of von Braun and his team, but informed by the aeronautical rocket research that Operation LUSTY had preserved. By the 1960s, most of the aircraft captured during Operation LUSTY had been scrapped, destroyed in testing, or relegated to museums. But their influence lived on in every jet aircraft flying. The Me-262s and AR-234s that had seemed so revolutionary in 1945 looked primitive compared to supersonic fighters and bombers, but they had shown the way forward. They had proven that jet propulsion was practical, that swept wings enabled high-speed flight, that radical designs could work. Every advance in aviation since 1945 built on that foundation. Colonel Harold Watson, who had led Operation LUSTY through those chaotic months in 1945, continued his career in the Air Force, eventually retiring as a brigadier general. He seldom spoke publicly about Operation LUSTY. Much of what his teams had done remained classified for decades. But he understood the significance of what had been accomplished. His teams had operated in incredibly difficult conditions, racing against time and Soviet forces, flying experimental aircraft that could easily have killed them, organizing a massive technical intelligence operation in the middle of a collapsing enemy nation. And they had succeeded beyond anyone's expectations, capturing not just aircraft but the entire body of German aviation research, preserving it for the benefit of Western aviation development. The pilots who had flown captured German jets carried those experiences throughout their careers. They had flown aircraft that were years ahead of anything their own nations could produce. They had seen the future of aviation firsthand. Many went on to become test pilots on American jet programs, bringing their experience with German jets to the evaluation of American designs. Others became advocates for aggressive aviation research, arguing that the only defense against technological surprise was to push the boundaries constantly, to explore every possible avenue of advancement, to never assume that what seemed impossible actually was. The German engineers who had cooperated with Operation LUSTY and later immigrated to the United States had more complex legacies. Some made significant contributions to American aviation and were celebrated for their work. Others remained controversial figures, their wartime activities casting shadows over their post-war achievements. The ethical questions about recruiting German scientists, particularly those who had been involved with certain political organizations or who had used forced labor in wartime factories, never fully resolved. American authorities made pragmatic decisions based on Cold War necessities, prioritizing technical expertise over moral judgment in many cases. This approach secured valuable knowledge but at a moral cost that historians and ethicists continue to debate. By the 1970s and 1980s, as many of the key figures from Operation LUSTY retired or passed away, the full story began to emerge through declassified documents, memoirs, and historical research. The scale of the operation became clear: hundreds of aircraft captured, thousands of documents preserved, hundreds of engineers interviewed and recruited. The impact on post-war aviation was undeniable. American jet development had leaped forward by years, perhaps by a full decade, because of the technology and research captured in those few months in 1945. Historians analyzing Operation LUSTY identified several factors that made it successful. First, timing. Watson's teams operated during a brief window when Germany had collapsed but before occupation zones were fully established and movement was restricted. Second, expertise. The teams included pilots skilled enough to fly unfamiliar aircraft and engineers knowledgeable enough to recognize significant technology when they saw it. Third, logistics. Despite operating in chaotic conditions, they successfully moved aircraft and equipment out of Germany before it could be lost or captured by Soviet forces. Fourth, priority. Senior military leaders recognized the operation's importance and allocated resources accordingly. And fifth, perhaps most importantly, luck. They found aircraft relatively intact, discovered documentation that hadn't been destroyed, and encountered German engineers willing to cooperate. The Soviet parallel operation, though successful in its own right, faced different challenges. Soviet forces had captured different facilities and different engineers, giving them a somewhat different technological base to work from. Soviet aviation had been focused on different priorities during the war: rugged, easily maintainable fighters optimized for Eastern Front conditions rather than high-performance interceptors. Integrating German high-technology jets into this context required different approaches. The Soviets initially copied German designs more directly than the Americans did, producing engines and even complete aircraft that were essentially German designs built in Soviet factories. Only later did Soviet engineers begin developing distinctly Soviet designs that went beyond German templates. This difference in approach, American integration and adaptation versus Soviet copying and eventual divergence, reflected broader cultural and organizational differences between the two systems. American aviation companies were private firms competing for military contracts, which encouraged innovation and different approaches to solving similar problems. Soviet aviation bureaus were state organizations often focused on meeting specific requirements, which could lead to more conservative solutions that emphasized reliability and meeting specifications over breakthrough performance. Both systems produced excellent aircraft, but they did so in very different ways, and both were building on German foundations captured in 1945. As jet aviation matured in the 1950s and 1960s, new challenges emerged that German research hadn't addressed. Supersonic flight required understanding phenomena that German engineers had only begun to explore. The thermal loads on aircraft flying at Mach 2 or Mach 3 created materials challenges that demanded new ALAs and construction techniques. Radar and guided missiles changed air combat in ways that made some German innovations obsolete even as other principles remained valid. Jet engines evolved from the primitive turbojets of the 1940s to sophisticated turbofans with much better fuel efficiency and performance. But even as aviation technology advanced beyond what German engineers had achieved, the fundamental principles they had validated, swept wings for high-speed flight, jet propulsion for sustained high performance, careful attention to transonic aerodynamics, remained relevant. The commercial aviation revolution that began with the Boeing 707 in the late 1950s represented an indirect legacy of Operation LUSTY. The swept wings and jet engines that made mass air travel practical traced their lineage directly to German research. Before World War II, transatlantic flight was a luxury available only to the wealthy, accomplished in propeller-driven aircraft that took many hours and offered minimal comfort. By the 1960s, jet airliners could cross the Atlantic in hours, carry hundreds of passengers, and do so safely and reliably. This transformation of human mobility, which has reshaped global commerce and culture, built on technological foundations laid during World War II and preserved by operations like LUSTY. The environmental impact of jet aviation, noise pollution, carbon emissions, contrails affecting climate, represents the dark side of this technology revolution. German engineers developing the Me 262 in the 1940s weren't thinking about environmental consequences. They were focused on military performance. But the jet age they helped create has had profound environmental effects that we're still struggling to address. Modern efforts to develop more efficient engines, alternative fuels, and eventually electric or hydrogen-powered aircraft are attempts to preserve the benefits of jet aviation while mitigating its environmental costs. This challenge, maintaining mobility while reducing impact, represents the next phase in aviation's evolution, one that will require innovation as significant as the jet revolution that Operation LUSTY helped enable. Looking at Operation LUSTY from today's perspective, several themes emerge. First, the operation demonstrates how warfare accelerates technological development. The Germans developed revolutionary aviation technology because they were desperate, because they were losing, because conventional approaches weren't sufficient. Desperation drove innovation in ways that peacetime research rarely matches. Second, the operation shows how knowledge flows across borders and ideological boundaries. German research, developed to help one side win a war, ended up benefiting both sides in the Cold War that followed. Technology, once created, escapes its creator's control and spreads to whoever can capture, understand, and apply it. Third, the operation illustrates the importance of technical intelligence. Understanding what adversaries have developed, what they're capable of, and what principles they've discovered is as important as developing your own technology. Watson's teams didn't just capture aircraft, they captured knowledge, and in the long run, that knowledge was more valuable than any physical hardware. Fourth, Operation LUSTY demonstrates the ethical complexities of technological competition. Recruiting German engineers meant overlooking or minimizing their wartime activities, prioritizing American Cold War interests over justice for those who had suffered under the German regime. These weren't easy decisions, and they've generated legitimate controversy. but they were pragmatic decisions made by leaders who believed that denying the Soviet Union access to German expertise was more important than punishing every individual who had contributed to the German war machine. History doesn't offer clear moral guidance on whether these decisions were right or wrong, only the recognition that they had significant consequences that shaped the post-war world. Fifth, the operation shows how individuals can have outsized impact in moments of historical transition. Watson and his relatively small team of pilots and engineers, operating for just a few months in 1945, influenced aviation development for decades. Their willingness to take risks, their technical expertise, their organizational skills, and their understanding of what was important, all of this mattered enormously. In the chaos of Germany's collapse, when the old order was disintegrating and the new order hadn't yet crystallized, small groups with clear missions and adequate resources could accomplish things that would be impossible in more stable times. The aircraft that survived from Operation LUSTY, the Me-262s in museums, the documents in archives, the photographs and film footage of those first American test flights, are physical reminders of a pivotal moment in aviation history. When visitors look at these aircraft today, they're seeing technology that was revolutionary in 1945 but seems primitive now. The Me-262's top speed of 540 miles per hour is slower than many modern commercial airliners cruise. Its engines, which seem so advanced, would be considered impossibly crude by current standards. But these aircraft represented a fundamental shift, the moment when aviation left behind propellers and piston engines and embraced jet propulsion and high-speed aerodynamics. Every advance since then has built on that foundation. Some historians have speculated about alternative histories. What if Germany had deployed jets earlier in the war? What if they had produced them in greater numbers? Could jet fighters have prevented Allied bombing campaigns from devastating German industry? Could they have gained air superiority and changed the war's outcome? These questions are ultimately unanswerable, but they highlight the significance of German aviation technology. The Me-262 was genuinely revolutionary, and in different circumstances, it might have had much greater impact. That it didn't change the war's outcome was due to factors beyond the technology itself: resource shortages, strategic mistakes, Allied numerical superiority, and the fact that by the time jets arrived in significant numbers, Germany was already losing. But if German jets didn't change World War II's outcome, they certainly changed post-war aviation. And Operation LUSTY was the mechanism that ensured German research wouldn't be lost or monopolized by the Soviet Union. By capturing and preserving that research, by documenting it and making it available to American engineers, Watson and his teams ensured that the jet age would arrive in the West with all possible advantages. They gave American aviation a head start in the Cold War competition that would dominate the next 4 decades. As we stand today, more than 80 years after Operation LUSTY, we can see its legacy all around us. Every commercial jet aircraft flying overhead carries swept wings derived from German research. Every military jet fighter uses aerodynamic principles that German engineers validated. The global air transportation network that connects cities and continents, that makes it possible to have breakfast in New York and dinner in London, that has reshaped human geography by making distance less relevant. All of this traces its lineage back to the jet age that began with German innovation and was propagated worldwide through operations like LUSTY. The story of Operation LUSTY is ultimately a story about the dual nature of technology. It can be developed for destruction but applied for benefit, created by one nation but used by many, intended for one purpose but adapted for others. The German engineers who designed the Me-262 hoped it would shoot down Allied bombers. Instead, their work led to the Boeing 707 and global air travel. They hoped to develop weapons that would help their nation win a war. Instead, they developed technology that would benefit humanity worldwide, albeit with environmental and other costs that we're still calculating. Technology escapes its creator's intentions, and Operation LUSTY was the mechanism by which German aviation technology escaped German control and became part of humanity's common technological heritage. Colonel Watson stood on that German airfield in April 1945 and saw the future of aviation. The Me-262 before him wasn't just an enemy aircraft, it was a glimpse of what was possible, what was coming, what would inevitably transform military and civilian flight. His decision to fly it, to understand it, to capture it and share that knowledge with American engineers, was one of many such decisions made during those chaotic months. But collectively, those decisions shaped the world we live in today. The jet age was coming regardless. Too many engineers in too many nations understood the basic principles. But Operation LUSTY determined when it would arrive, who would benefit first, and how quickly it would transform from revolutionary to routine. That may be the operation's most important legacy, not that it gave the West German technology, but that it accelerated aviation's evolution, compressed decades of potential development into just a few years, and ensured that the future arrived sooner than it otherwise would have. And in doing so, it changed not just aviation, but the world.